Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very happy to have Julia Truzoi tell us about allocating goods to maximize fairness.
Thank you. Yeah, so I'll be talking about allocating goods to maximize fairness. And this is joint work with Deeparnab, Chakrabarty, and Sanjeev Khanna. So I will first just describe the problem that I'm going to talk about this whole talk. The problem is called Max-Min Allocation. So in this problem, we have a set A of M agents and a set I of N items. So basically, agents want these items, and we need to decide how to allocate these items to the agents. So for every agent A and item I, we have a utility UAI, which is how much this agent values this item, or how happy the agent is going to be if it gets this item. And so we assume that these items, they're indivisible, so each one of them has to go to just one of the agents, and we have just one copy of each item. So what we need to do is for each one of the items to decide who gets it. Once we decide on the allocation for every agent A, the utility of this agent, or how happy this agent is simply the summation of its utilities for the items that it received. So the utility function is additive. And the objective function is basically we want the least happy agent to be as happy as possible. So we want to maximize the minimum utility of any agent. So I'll just say a word about notation, and then I'll go back to this problem definition. So throughout this talk, M is the number of items, M is the number of agents. And in general, they can be very different, but you know, for the sake of this talk, you don't really have to remember which one is which, just you can think about them being of the same order of magnitude. I just wanted to say that they can be very different. So here is an example of problem input. Here we have 3 agents, and we have these 4 items.
It's only interesting when the number of items
is more than, more than number of agents, obviously. Yeah. But it could be much, much more. So here's an example of a problem input. We have these 3 agents and 4 items. So when there is no edge between agent and item, it means that utility is 0. And when there is an edge, the number on the edge says what is the utility. So for each one of these items, we want to decide who is going to get it. How do we allocate these items? And for example, we can decide to allocate them according to these red edges. So once we found an allocation, we compute what is the utility of the agents. So the utility of the first agent is 6. Of the second is 3 plus 1, it's 4. And of the third is 5. So the least happy agent is the second agent. Its utility is 4. And this is the value of our solution. So this is the number that we want to be as high as possible, the utility of the least happy agent. So let me say you a few words about this problem. So one can think about a number of ways what it means for allocation of goods to be fair. It is not a trivial question in offline scenario, but I guess this is one of the standard ways. And this problem is somewhat related to the k-cutting theory, which is an area where the basic question that people are asking there is how to allocate resources to people in such a way that every player believes that this allocation is fair. So this is a problem of a slightly different flavor, of course. And normally, these problems have been studied in the setting where the goods or the items are divisible. So you can cut the item into as many pieces as you want. And the problem is, in this setting, is studied really a lot. There are whole books written on it. But when the items are indivisible, when each one of them has to go to just one person, then this problem is really poorly understood. And probably one of the basic difficulties is that this problem seems to be really difficult computationally. is not very well understood computationally. So the problem is not surprisingly NP-hard. And we're going to still try and handle it by using approximation algorithms, which also happens to be my research area. So just to remind you, when we have an NP-hard problem, approximation algorithm is, first of all, efficient algorithm. We want it to run polynomial time. And also, it gives us some guarantee on the problem, on the solutions it outputs. For instance, if for any problem instance, it always outputs a solution whose value is at least opt over alpha, opt is always going to be the optimal solution value, then we say it's an alpha approximation. Okay, so an alpha approximation algorithm, no matter what input we give it, it has to output a solution whose value is at least opt over alpha. And in the area of approximation algorithm, this alpha, this approximation factor, is one of the main ways we measure how good an algorithm is. There are, of course, other parameters, but this is like one of the central ones. So we want this alpha to be as close to 1 as we can, so we get a solution as close to the optimal as we can. And sometimes we are pretty lucky. We can get like a 2 approximation, 3 approximation. That's considered lucky. Sometimes we are less lucky, and we get approximation that's a function of the problem input size, like log n, which is even still considered pretty good, or root n and things like that. Yeah, so alpha is approximation factor. So before I go into what is known for the Max-Min allocation problem, I want to mention one special case of the problem called the Santa Claus problem. And one reason that I mention it is that it's a really, really well-studied special case that has a nice, interesting history. So it's basically the same problem, only we have kids instead of agents, and we have presents instead of items. And now every kid needs to specify what is their utility for each one of the presents. So here is the difference. There is some restriction on how these utilities are allowed to look like. So every present is associated with a number, and the kid may decide if he or she wants this present or not. But if they do want it, then their utility has to be the number that's written there. So in other words, it's a special case of the Max-Min allocation problem where for every item, all edges that are incident on this item, all of them have the same number written on this edge. So this is a pretty restricted special case of the problem, and even this is really non-trivial. It has actually a long and interesting history that I don't want to get into. I'll just say that the state of the art after all this work is that there is a constant factor approximation algorithm. I don't think that this constant factor was ever actually computed. It's probably pretty big. I would guess like 50. But this is all I wanted to say about this problem. And now I want to go back to the general Max-Min allocation problem. So the first approximation algorithm to this problem due to Bezukova and Dani was n minus m. N is number of items, m number of agents approximation. That's pretty bad if n is more than m. And the state of the art prior to our work is a root m approximation. The tilde there hides some poly-logarithmic factors. And that was all that was known about this problem. Now we can ask, maybe it isn't hard to get a good approximation for this problem. Maybe we can get some negative results. Well, all that is known even to this day is that this problem is NP hard to approximate to a factor better than 2. And even that is for very, very restricted special cases of the problem. So this is really a huge gap. It's almost as big as they go for a pretty basic problem. So the result that I'm going to show today, it gets a kind of trade-off between how good approximation factor we get and the running time of the algorithm. So we get n to the epsilon approximation in time n to the 1 over epsilon. And again, a tilde here hides poly-logarithmic factors. So in particular, if we push epsilon as far as it will go, you'll get poly-logarithmic approximation quasi-polynomial time. That's n to the log n time. A poly-logarithmic approximation. If we insist on getting efficient algorithms, then for any constant epsilon, we can get n to the epsilon approximation. So these are the results. And now one interesting aspect of this result, a technical contribution, is that we use a linear program that has a really, really large integrality gap, but we still manage to get a much better approximation even though we use it. So let me just, I'll just take a little bypass and I will say a few words what it means for LP to have a large integrality gap and why this is surprising and different from usual approximation algorithms. So one of the standard ways to get approximation algorithms is by a technique called LP rounding. So this is the space of our feasible solutions for our problem, and we want to optimize over this space. We want to find the best possible solution, but this is NP hard. So what we can do is to write a linear program called LP relaxation for this problem, such that all our feasible solutions are still solutions for this LP, but it may include more solutions. Now, a good thing about linear programs is that we can solve them efficiently. So we can optimize over the space of LP solutions efficiently. That's the good thing. The bad thing is that we may end up getting a point that lies outside the feasible region, right? Not really a solution that we want to get. Still, because LP solutions include our feasible solutions, we know that they can be only better. So the optimal of LP is at least as good as the optimal solution. So if we compare ourselves to opt-LP, we're always pretty good. It's as good as comparing ourselves to real opt. So the optimal of the LP solution is called fractional solution, and a real optimal is called integral solution. So once you solve the LP, you get an optimal LP solution, but it may lie outside the feasible region. So after that, what you want is to take this solution and somehow to convert it into a real solution to a real problem. And this process of converting the solution is called LP rounding. This is where exactly the approximation algorithm part comes in. So if you manage to convert LP solution to a feasible solution and you don't lose too much on your solution value, then you will also get a good approximation algorithm. So a standard procedure to getting approximation algorithms through LPs is you take a problem instance, a fractional LP solution, and then you run this LP rounding algorithm that gives you integral solution. Oops. And now, if when you do this rounding, you only lose a factor alpha in your solution value, then you get approximation algorithm whose approximation factor is alpha. So this is like a really standard paradigm how LP rounding is used to get approximation algorithms. So now, what happens if we manage to find a problem instance in which optimal LP solution is very, very far from optimal integral solution? They're within root m or bigger factor. And now, if we manage to find such an example, it shows that this scheme, you cannot use it to get a root m or better approximation algorithms, simply because you will not be able to output an integral solution of this value, opt-LP over root m, because it doesn't exist. Because the gap between integral and fractional solution is just too large. So normally, if we find such an example, we call it a root m integrality gap example. And in the area of approximation algorithms, once you get this large integrality gap example, this is the end of the way for this LP. What you will do, you may try to improve this LP, write a different LP, try to switch to a different technique. Maybe you want to do SDP rounding, maybe something else. But as far as this LP goes, this is it. Now, I should say that it's not that we choose to use an LP that has this large integrality gap. All LPs that are known for this problem, that were used in literature for this problem, have this large integrality gap. And still, we managed to get a much better approximation, even though we use this LP as our building block. So let me just say also another thing. So there is all this m there, m here. So basically, we get the same results in terms of m to the epsilon, except that the running time is going to be quasi-polynomial. So before I continue with this result, I just want to mention independent work by Bhatteni, Charikar, and Guruswamy. So they looked at a special case of this problem, and they get similar results. The special case they looked at is where all utilities are 0, 1, or m, and the optimal solution value is m. And if we look at this graph of agents and items, and we ignore all edges that have utilities 1 on them, then they look at the following two special cases. One, if the degree of every item in this graph is 2, and the other is where this graph contains no cycles. So for both these special cases, they got also n to the epsilon approximation in n to the 1 over epsilon time. So I'll just say a few words. So these were independent results. I'll just say a few words about how they're similar and how they're different. So the LP relaxation that they use is not exactly the same as ours, but it's in the same spirit. It's the same idea. And this LP has a root m integrality gap, but for some special cases, the integrality gap becomes much better. And these are the cases that they managed to solve by using LP rounding of that LP. So now I want to focus on our results. And to make the presentation simpler, what I'm going to do, I will make this first assumption, but not these two. So I will assume that all utilities are 0, 1, and m is the optimal solution value. I will talk a little bit about this also later. But it turns out that if you make this first assumption, you don't make these two assumptions, you only make the first one, it pretty much captures the difficulty of the problem. And once we solved the problem with this assumption, it was not that difficult to extend it to the whole problem. So just to keep the presentation cleaner, I'll just do that. So again, we assume that all utilities are 0, 1, and m. And we are guaranteed that the optimal solution value is m. So if we look at this graph of agents and items, there are only two kinds of edges here. Black edges will always be utility 1 edges, and red edges utility m edges. So we're going to say that an item is light for some agent if this agent has utility 1 for this item. So it wants many of them to be happy. And we say that it's heavy for an agent if it has utility m for that item. So even one such item will make it happy. And obviously, the same item can be light for some agents and heavier for some other agents because all of them want it with different utilities. And now we said that we assume that the optimal solution value is m. And now what does it mean? How will the optimal solution look like? So for every agent, there are only two ways to satisfy this agent. Either it gets one item for which it has utility m, one heavy item, or it has to get m light items, m items for which it has utility 1. So if we look at the optimal solution for every agent, this is what is going to happen. And now what we want is to get an alpha approximation for this problem. So how will an alpha approximate solution look like? So here is where we relax it. In an alpha approximate solution, every agent will either get one heavy item, or instead of m, it will get m over alpha light items. If we manage to do this, this will be an alpha approximate solution. So I'm going to do one more kind of pre-processing step. I will assume that our instance looks in a certain way that's called canonical instance. And after that, I will show you that this is without loss of generality because any instance is easy to convert into this canonical instance. So it's not really a real assumption. So what is this canonical instance? In canonical instance, we have only two kinds of agents that we call them heavy agents and light agents. A heavy agent, all items that it wants with utility m. So these are the only items it wants. If it gets any of these items, it's going to be happy. A light agent, the opposite is true. All items it wants with utility 1. So it wants m of them, except that there is this one extra item that it wants with utility m. And this one extra item, it's a special item for just this light agent. So another light agent will have a different such item. The only thing is that these items, well, it's a special item for this agent, but it's possible that this guy will also want it. Right? Otherwise, it would be too easy. So these are the canonical instances. We make this distinction. We have only these two kinds of agents. And let me just show you really quickly. It's really easy to see that you can take any instance and turn it into a canonical instance. So here we start with any instance. We have this one agent that has some red edges and some black edges incident on it. So what I'm going to do, I'll split it into two agents, a heavy agent and a light agent. The heavy agent will take all its red edges, and the light agent will take all its black edges. And then I'm putting this extra item there that both of them want with utility M. So what is going to happen is here, if this agent is satisfied by a heavy item, then we'll satisfy this guy with the same heavy item, and this item will go here. If this one is satisfied by light items, then we'll satisfy this one with the same light items, and this thing will go here. So in this way, you just split any agent into two agents, and you get this canonical instance that's just easier to work with. Now we're ready to start with the algorithm. So the first idea and the first insight into this algorithm is that we start with a Max-Min allocation problem, and we turn it into a network flow problem. So the way we're going to do this is, first I'm going to give some agents some items. I will call them private items for these agents. But this is not a final assignment. This will make these agents happy, but some other agents will not be happy. After that, I'll define a flow problem in a corresponding network where we're going to reassign these items in such a way that everybody is happy. So in this way, we'll take the Max-Min allocation problem and define a flow problem. So let me first tell you how you get this allocation of private items, which is pretty simple, and then we'll talk about the flow problem. So remember, we had these black edges that have utility 1 and red edges with utility M. So we're just going to ignore the black edges, and pretty much we're going to take some matching on the red edges, and we'll say that this is a private item for this guy, and this is a private item for this guy. Obviously, we don't expect the simple algorithm to solve the whole problem. It's just a starting point. So an item will be private for at most one agent. Every agent will get at most one private item. And we only assign private item along red edges, so the utility has to be M. And I'm going to make another additional requirement that I want every light agent to get a private item. It's actually not so hard to do, because if you remember, every light agent had the special item for which it has utility M, and each light agent has a separate such item. So what I'm going to do is, for each light agent, this will be its private item. I just defined it beforehand. And now what happens with heavy agents, some of the items are already assigned, so now we'll just take the remaining items and we'll define some maximal matching between the remaining items and the heavy agents. This will be our assignment of private items. So once we do this assignment of private items, the people who got private items are very happy. They have utility M. But we don't expect this to succeed so well, so there will be some people who are unhappy and they did not get any items. And we call these people terminals because they're unhappy and because we're going to send flow to them. So there are also some items that we did not assign to anybody. And these items, we think about them as being source vertices. So in the network, we're going to send flow from the source vertices towards these terminals to satisfy them. I still did not define the flow network and how we compute this, what is a feasible flow. So let me just recap this more formally. So if every agent got a private item, we are done. Terminals are heavy agents that did not get any item, and S is the source vertices, the set of items that are not assigned to anybody. So now what we want to define a flow problem that will somehow do reassignment of these items to make everybody happy. And it's very intuitive and simple. How do you reassign items? Well, an agent will only release its item, its private item, will only give it away if it is satisfied by other items, right? So it will only send flow towards its private item if it received enough flow from other items to make it happy. This is going to be the rule for the flow network that I'm going to define in more detail. But our goal eventually is to make all the terminals happy and to keep all the other agents still happy. So the flow network, we just start with this bipartite graph of agents and items. I'm going to direct some edges in some ways, and I'm going to define the rules of the flow, which are very intuitive. For example, let's take a heavy agent that has a private item. So we direct all edges like this towards this agent and towards the private item. And the rule is going to be it only releases its private item if it's satisfied by a different item. So it only sends one flow unit towards its private item if it receives one flow unit from somebody else. Remember that all these items, it has utility M for them. And now for a terminal, we direct all edges towards the terminal. And all we ask is that it is satisfied. So it has to receive one flow unit. Right, so far it's a standard flow. Here is where the non-standard rule comes in. So let's say that we have a light agent. Remember, it has utility M for its private item, but utility is 1 for these items. So the rule is going to be it has to receive M of these items in order to release this one. So it will send one flow unit if and only if it receives M flow units. And finally, we just take this at a source vertex and we connect it to all items that were still not allocated to anybody. So if you think about this, this is a simple single source, multiple sinks flow problem, except that you have this really funny rule here, that some vertices, they have to receive M flow units to send one flow unit. And then you have the standard rules. Well, at most one flow unit leaves any vertex. And there is a conservation of flow on items. And finally, we want to find integral flow that satisfies all of this. Okay, I don't know if it helps you to think about this way, but one way to think about it is that what we want is for an edge to carry one flow unit if and only if it lies in the symmetric difference of the optimal solution and the assignment of private items that we have found. This is going to give you feasible flow. If you don't like this definition, then another intuitive definition is that if we don't send any flow through an agent A, that means that its assignment of private item is the final assignment. We don't need to do anything. If a flow is sent through an agent, then everybody who sends flow to this agent, each one of these items is assigned to this agent, but not its private item. So this is another interpretation of this flow. But the point is, it's not so hard to see also from this thing, is that if really the optimal solution value is M, then the flow with all these requirements has to exist, no matter how we assign the private items. Simply because, you take the symmetric difference and that's it. So we want to solve the flow problem, but we want to solve it approximately. What does it mean? How do we solve the flow problem to get approximate solution? The way we relax it is here. So this guy, instead of receiving M items, if it receives M over alpha items, it can send one flow unit out. Then it will still be an alpha approximate solution. So if we find this alpha relaxed flow, relaxed in the way that I just showed, then this will give us an alpha approximation. So what happened here is that we started with a Max-Min allocation problem, we turned it into a flow problem, and now it's enough to find this alpha relaxed flow solution to get a solution to the whole problem. So what I'm going to do now is I'm going to show you yet another view of this problem that is kind of complementary to these two. So a question that I'm going to ask is, let us look at the optimal flow solution, the integral flow solution, and we're going to only look at edges that carry one flow unit. How will that solution, how will that graph look like? So the way this graph is going to look like is we're going to get a bunch of structures like this. I'm going to explain what the structures are, but basically each such structure starts from a source vertex, ends at a terminal vertex, and is used to send flow from the source to this terminal. So what I'm going to do, I'll just delete the source to make the structures trees, right? They are basically trees if it wasn't for the source. So if we take all edges that have flow of one of them, and we erase the source, what we get is a collection of trees like that. This is a terminal. Each one of these internal vertices is a light agent. It has to receive m flow units to send one flow unit out. Now, each one of these edges is really not an edge. It's a flow path that starts with a light agent, ends at a light agent or a terminal, and it goes item, agent, item, agent. All of these agents are heavy agents. So this is like a standard flow path. Because it's like a standard flow path, it's easy to kind of think about this as being an edge, but those are not really edges. Those are flow paths.
But these paths, are they necessarily disjoint?
Yeah, they have to be disjoint, yeah. Because you remember every agent can only receive one flow unit and send one flow unit. Every item can only receive one flow unit and send one flow unit, yeah. Yeah. So your optimal solution, if you take the optimal integral flow, it will be a collection of trees like that. So instead of looking for a flow solution, the same thing is basically really the same thing, as we want to find a collection of disjoint trees like that. So we want to find one tree for each one of the terminals, because this is how we're going to satisfy the terminals by sending the flow to them. And once we find this collection of disjoint trees of one tree per terminal, the value of the solution is going to be the minimum degree of any one of these light agents.
So there can be many layers of those light agents, right?
Yeah, I was exactly going to say this. Yeah. So what happens in a real optimal solution, the tree does not have to look this nicely, right? It doesn't have to have all the leaves at the same level. And yeah, it can look in any which way, which is bad for us. I'm going to tell you later why. But basically, what we do, there is a way to cut this tree in such a way that all the leaves do lie on the same level. So they do look nicely like that. And if all we want is n to the epsilon approximation, we can also make this tree pretty shallow. We can make the height to be 1 over epsilon. This is something that we are going to use later. So if all we want is n to the epsilon approximation, we can make the tree's heights to be 1 over epsilon. And this is the only place, basically, where we lose this n to the epsilon factor.
So, I mean, you're really assuming that all the leaves are exactly the same level, not just
I'm just going to cut. Yeah, yeah.
But I mean,
no, so
you just have some at level 1?
Oh, sorry. So you can take the optimal solution and you can cut it in such a way that for each one of the trees, the leaves are going to be at the same level, but it's possible that there will be one tree of height 1, another tree of height 2, and so on. Yeah, but the maximum height is going to be at most 1 over epsilon. Okay, so the algorithm, the real algorithm, consists of 2 parts. First, there is a linear programming relaxation and its rounding. And the second part is where we use this first part pretty much as a black box to get a good approximation. So because I don't have much time and I want to spend a little bit more time on the second part, I'll just say, I'm not going to write the LP, which is pretty complicated. I'll just say what it does and what LP rounding gives us. So remember, we wrote this flow network and we wrote all these flow constraints. So these flow constraints, it's very easy to turn them into LP constraints. This is how flow constraints are. And this can give you an LP, but this LP is easy to see, it's no good. It's basically impossible to get anything from there. So what we need to do, we need to work a little harder. And what we actually do is that for each H tuple of light agents like this, we're going to have a separate variable in the LP. And so because of this, the size of our LP is going to be n to the height of the tree, which is why we wanted the tree to be really shallow. H is going to be 1 over epsilon. And even after we do that, the integrality gap still stays root m. So it may look like we didn't do much. But there is one advantage that we can get from this LP is that we can do LP rounding. This LP rounding gives us polylog n approximate solution. It cannot be a feasible solution because the integrality gap of the LP is root m. It is something that we call almost feasible solution. So I'm going to explain to you what exactly it is. Okay, so remember that what we wanted to get eventually is a collection of completely disjoint trees where for every terminal there is a separate tree. And we wanted the in degree of every vertex here to be m. So first of all, we will not get in degree m. We're going to get in degree m over alpha, where alpha is polylog n. But this is something you would expect from an alpha approximate solution. This would be good if this was all. This would give us a polylog n approximate feasible solution, which we can't expect to get. So there is something that is going to be not quite right with this solution. So notice that I color these edges in 2 different colors. There are green edges and blue edges. So the green edges are edges that send flow to light agents, and blue edges, they go directly to the terminals. So instead of a collection of completely disjoint trees, we're going to get a collection of trees that are almost disjoint, but not quite. In what sense? Some items, they will appear once on the blue path and once on the green path. So it could be a blue path and a green path in the same tree, or a blue path and a green path in different trees, but it will happen. So it really sounds it's not such a big deal because we are really, really almost there. But it has to happen because the integrality gap of the LP is root m. There is no way you could get a collection of disjoint trees with really in degree m over polylog n and trees being completely disjoint. So this almost disjointness, this little thing, it has to happen here, which is why this LP will never give you this polylog n approximate solution. So there is one thing only that I wanted to mention here that kind of will be maybe useful later. It will be useful later. So the distinction between these green edges and blue edges is actually a big distinction in the following sense. So if you look at any of the guys here, even if it loses half of the incoming flow, things are still good. So our solution value will go down by factor 2. So what, right? But these terminals, each one of them has 1 flow unit coming in, and there is nothing you can do about it. So in some sense, these green parts, they're a lot more flexible than the blue parts. For example, if a vertex would appear on 2 or 3 green edges, it would still find a way to recover some good solution from the green part. But if a vertex appears one on the green edge, one on the blue edge, there is nothing you can do because this blue thing, this terminal has to get this 1 flow unit. There is no way to compromise there. Okay, so we will use this distinction between this more flexible green part and the inflexible blue part later.
Once again, this blue edge is really a flow paths.
Yes. Yeah. Yeah. So I will now focus on the second part, how we use this LP rounding as a black box to get a good solution. So we started with the integrality gap of this LP being root m. Now, what does it mean that the integrality gap of the LP is root m? It means that for some inputs, the gap is large. For some, it may be small, right? Now, what is an input to the LP? An input is our flow network. The flow network, the way we built it, we started with a problem instance and an assignment of private items. Problem instance we cannot change, right? But assignment of private items, maybe we can tweak it in such a way that the integrality gap of the LP goes down. So that's the question. Actually, there is like one reason to be hopeful is that even though the integrality gap of the LP is root m, it's not larger than the number of terminals, guys with no private items. So it looks like if we could find just a better assignment of private items so that more people are happy, we have fewer terminals, the integrality gap will go down. And it actually will. The problem is that the way we assign private items, we found some matching, right? And the maximum matching that you will find is the best you can do. The number of people that will become terminals is, there is no way to get around this. So basically, there is a limit how much you can push it, and this limit is your maximum matching. So it looks like this plan does not quite work. Let us try another way of reducing the number of terminals. So this time what I'm going to do, I will find some subset of agents to which I will find an assignment of items. And then I will take these agents and pull them out of this instance. I will pull the agents but not their items. Now that we have fewer agents, their private items are up for grabs. We will be able to assign more private items to more people, and we'll get fewer terminals. So I don't know how it sounds to you. Well, the good news that, this way, if you pull some people from the game, obviously you'll have more private items to go around. Obviously, the number of terminals will go down. But we have a problem here that we pull out people, but we don't pull out items, right? So I found an assignment of some items to these agents. I pull these agents out, but then I gave their items to somebody else. And actually, we want to do a number of iterations like that. Each time I pull some agents out, but not their items, and so on. So there is a problem here. The thing is that in some situations, even if you assign an item several times, you can still recover a good solution. In some other situations, if you assign an item even twice, then you're dead and you cannot recover anything. So what we want to do here, when we pull out these items out of the instance, we want to make sure that we are in the first scenario. The assignment that we found for these agents is such a nice assignment that even though we assign these items several more times, we will still be able to make everybody happy. So let me show you an example. So let us say in the first iteration, this agent got this item for which it has utility m. And then I take this agent, pull it out over the instance, and give this item to somebody else in the second iteration. In this case, things are really bad, because eventually only one of them can get this item, the other one will get nothing. This will give us a really bad solution, because we are looking at the least happy agent. This is not a nice assignment. If we look at another scenario here, so first, in the first iteration, we took all these items, assigned them to this agent. It has utility 1 for all of them. In the second iteration, let's say we took the same items and assigned them to somebody else. So this is a pretty good situation because they can just share these items. Each one of them will get half the items, but we will still get a reasonable solution. So this is nice. So this is where we want to be. We want to be in a situation where even though you assign the items a couple of times, you can still recover a good solution. Well, this is like way too simplistic. We will not be able to make assignments like that. We'll have to do something a little bit more complex. And so what we want to do is we are back to these trees. We want the trees to be completely disjoint. So we want to find a collection of trees that are completely disjoint. Because we really want them to be completely disjoint, we will not find a tree for every terminal, only for some terminals. But then once we find a collection of trees like that, I think about the green part of this tree as being the assignment to this agent. This is my witness that it's possible to satisfy this one agent. So I'm going to pull this agent out, and now it's private item. It doesn't need it anymore. I can reassign it along this path, so this stops to be a terminal. Let me show this in a little bit more detail. So if we find a collection of disjoint trees, even though not every terminal will get a tree, but many of them will, we'll just take this one agent and pull it out of the instance, and we'll remember this green part of the tree. Remember, we said that the green parts are really nice in the sense that even if some items appear in several such trees, we can still recover something. So we'll think of this green part as a nice assignment to this agent. And now this agent A, it doesn't need its private item anymore. So if we look back at this blue path, so this is the private item of A. This is the private item of this guy. Now A doesn't need this private item anymore, so we can give it to this guy. And then this private item goes to the terminal, and the terminal stops being a terminal. It now gets a private item. Okay, so if we manage to find many such trees, then many of the terminals will stop being terminals, and then our LP integrality gap will go down because we'll have fewer terminals. Which is a good thing, but how do we find such an assignment? How do we find this collection of disjoint trees? And the answer is that through LP rounding. So at this point, I guess you're pretty confused, so let me show you the whole picture, because it's kind of circular. So you start with a problem instance and assignment of private items. You run the LP rounding. You don't want to get a solution from this LP rounding. All you want to get is a nice assignment for some subset of agents. Now, if you manage to do this, then you pull these agents out. Once you pull them out, you have more items to go around, so you can get a better assignment of private items. And this better assignment of private items becomes an input to the LP. First iteration finished. In the second iteration, you get a number of terminals went down. Again, all you try to do is to find a subset of agents to satisfy by using these trees. Pull these agents out. Now you can reassign their private items to, so the number of terminals goes down, and feed this assignment of private items back into the LP. And you continue like that. The thing is that the number of terminals goes down so fast that after 1/epsilon iterations, this whole thing stops. This is the epsilon from the n to the epsilon approximation factor. And in the end, because all this thing on the right, all this subset of agents, they were satisfied by these green trees, we can combine all these solutions together. Every item is going to be assigned only 1/epsilon times, so we can combine them together to get a good solution. So the only thing that I need to show you is how from LP rounding you can get this nice assignment of private item, of nice assignments of items to a subset of agents.
I'm a bit confused. What happens with the alpha during this loop? I mean, you fixed it
alpha.
in advance, the final one that you were going to want?
Yeah. So you're going to lose a little bit. So first of all, in each iteration, the LP rounding, what it produces is alpha equals polylog n. So you lose a little bit there. And then when you combine all these guys together, you will also lose a little bit. But the thing is that the whole procedure, it only loses you polylog n factor. Where you lose n to the epsilon is where you cut these trees to be shallow. Okay, so what happens here, we say that LP rounding gives us almost feasible solution, meaning that we get a collection of trees, we get one tree per terminal, but some items may appear twice, once on the green path and once on the blue path. What we want to get our nice assignment, nice partial solution, is we want to have a tree for each one of the, we want to have the trees completely disjoint, but now we don't care if not every terminal gets a tree. We just want many of them to get a tree. And also, okay, this is another place. If you lose a little bit on the min degree of a light agent, then it's also fine. I mean, you will accumulate some factors in your approximation ratio. How much more time do you have? 5 minutes. So should I skip this part? I guess I'll skip this part, and I'll just I'll just show that this is not a very difficult step to do. It's a okay. Oh, I guess I'll just skip this part. And so this is the whole scheme of the algorithm. So the way the LP rounding is used is in this step to find this partial assignment. And then in every iteration, the number of terminals will go down and the integrality gap will go down. So conceptual view of the algorithm. So we started with a problem instance and an assignment of items, private items. And the integrality gap for this instance was really large. So what we have done throughout this algorithm is we have produced a series of subproblems. And for each subproblem, so these subproblems, they become smaller and smaller. For each subproblem, a different assignment of private items. And the integrality gap just went down in each one of these iterations. And the way we produce each one of the sub-instances is by LP rounding of the previous instance in the LP. And of course, each time we have pulled some of the agents from the instance and fixed their assignment. And in the end, we just need to combine all these assignments that we have for the agents that we have pulled out. So to summarize, this problem is still very much open, and so we get into the epsilon approximation and into the 1 over epsilon time, poly-logarithmic approximation, quasi-polynomial time. The current hardness approximation is 2, and this hardness approximation holds for very, very restricted instances. So this is a really large gap. And another interesting question is whether this kind of idea of getting around the integrality gap of the LP can be used elsewhere. Because there are many problems on which we are stuck with LPs and semi-definite programs for which that have large integrality gap, and we don't know what to do with them. So let me now just say a few words about my research. So my research area is basically approximation. I do both approximation algorithms and also lower bounds, like hardness approximation results. And so I do just both of them at the same time. I sometimes take a problem and you don't know where you're going to end up, and I find it really useful to play between these two things. So one of the main parts of my work is problems on graphs. So things like cuts and flows, graph decompositions, graph routing, network design, and so on. So I have spent a lot of time on these things, and I keep coming back to them. And in turn, I find that these things are really useful in so many different problems. I also worked a little on scheduling and some problems that have more geometric flavor. As an example of such a problem, I worked on a maximum independent set of rectangles in the plane. And sometimes there are problems that they just don't fall into any category. So last year I spent a lot of time on the graph crossing number problem. And basically any problem that comes up and is interesting is interesting. And you can sometimes find really surprising and interesting connections. For example, for this problem, I had to use a lot of graph decomposition, cuts and flows things.
Actually, can you spend a minute just stating what is the graph crossing number?
Yeah, it's easy to state, hard to solve. So it's about, this is basically, there is a whole area that's called graph drawing, and this is the problem there. You want to draw a graph, which means a vertex of a graph is going to be a point, and an edge is just a curve connecting the two vertices. And you want to minimize the number of points where two edges cross. This is the minimum crossing number problem. The approximation factor for this problem, well, before my work was n times log n. And now it's n to the 0.9. And this problem, like there is a whole area of computer science that only does this problem. Oh, OK. This was the end of the talk. Thank you. Oh, I don't know where I got here.
Questions? I have one question. So for the hardness, when does the hardness kick in terms of the difference of m and n? I mean, if m equals n and you're the mid, right, Max-Min matching is an easy problem. So.
Oh, I see. So you're saying so the hardness of approximation is, I think, when every item has degree 2 or something like that. So it's really low degree graphs, but the hardness is 2. We don't have any other hardness. And for when degree is 2, then I think there is a factor to approximation.
Degree is 2. But also, okay, but you're not looking for a matching there.
No. Yeah, there are actually some, you can set up some really simple instances, like families of instances that we still don't understand. Because in this algorithm, we lose like log after log a number of times. And each time we can ask, do we have to lose this log? And then you can set up a really simple instance where, we lose this log. And like it's very natural to try to either turn it into hardness approximation or, like log and hardness approximation. This is like one of my plans for a summer project.
Other question?
So very general sort of question. I mean, one obvious shortcoming of the basic problem of the Max-Min problem is, if there's one person who's just always going to be really badly off, no matter what you do, it means you're indifferent to all other improvements to everyone else, which could be. And if you're even just looking for an approximation algorithm, it sort of makes that even worse. So I'm just wondering, is there any tweak to the problem that messes that and is still makes it a problem within the same class?
Well, like if you wanted like a by criteria to satisfy half the people and so on, or maybe sometimes you can use different norms instead of L infinity, the problem becomes much easier. The thing is that these max-min and min-max problems, there are several such problems that we just don't understand.
Right.
So I don't know if, like, even from theoretical perspective, this kind of makes them, like, we really want to understand them. But it's true that you can do better if you relax some of the requirements. And I totally agree with you that it's not clear from the point of fair allocation that this is the objective function. I agree with you.
Actually, in terms of approximating solution, it's an easy case. Because the optimum is very small, then it's easy to approximate. Just you have to make sure that you give this guy the right amount, and then the others you don't even. Even if you do a lousy job, then you're good. So it's actually an easy case in terms of finding a good approximation. So the hard cases are when actually there is a good assignment, and still you're not good.
Did you try finding some other linear program and try to fit this into a standard approach? There are like problems where the integrity gap is bad, but then you non-deterministically make some guesses, and the integrity gap improves. So did you try to do those things?
I'm actually not aware of this. I would be very interested in looking into this.
Then it might just fit in the standard paradigm, which is, I consider it's a strength, not a weakness, if something can fit into the
Okay, then I would be interested in hearing about it.
Okay, thanks, Julia.